All right, welcome everybody. Today we're talking about lesson number 94. This is day 2 of section 12.3, and we are still talking about the very important tangent line problem. The truth is today's lesson is very similar to day 1, so if you're all caught up to date, it should be quite manageable. Those are the 5 problems for homework tonight, so again, focusing on quality over quantity. The reason why I highlighted the last 2, both of those are ABC, so make sure you answer each part. The part that asks for a graph, you can just give an estimation. And then for part A, because it's asking you for the slope at a specific point, you're going to use the formula that's f of c plus h as opposed to x plus h. And I'll point that out again as we see that in our lesson. So first, a quick reminder of yesterday's lesson to kind of set the scene here. Remember that we are talking about what calculus actually means. And calculus is, of course, the study of rates of change of functions. And we are talking specifically about tangent lines to a graph. Now, if you're talking about any curve other than a linear function, if you're trying to just estimate the slope of the tangent line, you could choose some random points on the graph. And again, take a straight edge and kind of just try to approximate what the slope of that tangent line would be at any particular point. Again, comparing something like x1, y1 to x2, y2, you can clearly see that they both have positive slopes, but the one at x1, y1 is rising more quickly and would therefore have a steeper slope than it would at x2, y2. For something like x3, y3, that is where you have a horizontal tangent line. And the fact that a horizontal tangent line has a slope of 0 is going to become very, very important at the end of today's lesson. And then again, here at x4, y4, you can clearly see that you have some kind of a negative slope. And again, this is just how you would kind of eyeball it. Obviously, just eyeballing it in estimation is never going to be good enough for us. So instead, we are going to talk about approximating a tangent line by first using a secant line. Remember, of course, that a secant line intersects a function's graph twice, where a tangent line only does it once. So for any curve, you're going to assume 2 points. One of those, which is the point of tangency, xf of x, and then some second point, which is h units away, which makes it x plus h and f of x plus h. If you were to use your old friend, the slope formula, y2 minus y1 over x2 minus x1, and if you were to simplify it, that is what's called the difference quotient. So the difference quotient is shown here. And again, it really represents the slope of the secant line, which is what we abbreviate with msec. How do you take a secant line and turn it into a tangent line? Well, you do that by taking those 2 arbitrary points and moving them a closer, and closer together until they eventually become the same point. If instead of intersecting a graph twice, you're now intersecting it just once, then the secant line has now become the tangent line. How can you do that? How can you actually get closer and closer and closer to something? Well, that means you have to take the limit. So because the slope of the tangent line is equal to the limit of the slope of the secant line, that means that the slope of the tangent line is really the difference of the limit of the difference quotient. So that kind of summarizes everything that we did yesterday. And the truth is that today's lesson is very, very similar, except now we're going to get a new name for this process, and it's actually going to mean something. Before we get into that, just one quick reminder. Not only do we know that the tangent line is the limit of the difference quotient, but we have 2 different options. The first option is when you're trying to find the slope at a specific point, let's say the point 0.27 or the point 0.84, you would actually use whatever that x value constant is in order to solve the problem. Whereas if they just ask you for the general formula for slope, you're going to leave those x's as actual x's. And if you did virtual homework 19, which I'm sure you did, you'll see that that was kind of one of the main ideas, is making sure that you understood the difference. One of the most famous words in calculus, which again, I'm sure you've kind of heard it out on the streets, is something called a derivative. The truth is you have now been finding a derivative for a couple of days. You just didn't know that it was called that. So the definition of the derivative of a function at a specific point now has a notation. It looks like this, f with a little dash in the top. That is called f prime of x. So whenever you see that notation, that is how you say it, f prime of x. And from now on, what does it mean? It means the derivative, What is the derivative? Well, it's just a fancy name for what we've been doing. It's the limit as h goes to 0 of the slope of the secant line, or the limit as h goes to 0 of the difference quotient. So next year, when you get to calc, one of the first things Mr. Casey is going to ask you, or whoever your teacher happens to be, is going to ask you, what is a derivative? And I want those hands flying. I want some of you saying that it's the formula for the slope of the tangent line at a specific point. I want some of you saying that it's the limit of the difference quotient. I want some of you saying that it's the limit of the secant line formula. So you have to understand what a derivative is. Not only is there one definition, but there are actually several. So extremely important that you know that word derivative, extremely important that you know the notation for derivative, and extremely important that you know how to say it right, because you don't want to look like a clown. One very, very important note about rates of change. Again, rates of change is the main point of calculus. So the old formula for slope that you're used to, y2 minus y1 over x2 minus x1, this represents an average rate of change for a specific interval. So from the point 6, 2 to the point 8, 11. So the old formula for slope is the average rate of change, where a derivative is a formula for an instantaneous rate of change at a specific point. Again, I can't stress how important this difference is. Being an average means you're taking into account all the values over some interval. An instantaneous rate of change means it's just at one particular instant at one particular point. So that becomes more and more important next year, but it's kind of good to get a little preview. So how will the problems tonight differ from the problems last night? Well, the truth is you're going to be doing a lot of the same mechanics, but the problems are going to just be worded a little bit differently. So now it's going to say, find the derivative. Of course, this is the notation for derivative. And then I still have to give you the original function f of x. If you were paying attention to the past couple of slides, you will realize that the definition of the derivative is it's the limit of the difference quotient, which is the same formula that we've been using. Notice that because it's just asking you for the general derivative, we're leaving the x's as opposed to changing them to be specific values. So you're still going to do this same process. F of x plus h means go to the f function. Everywhere there's an x, you're going to put an x plus h. And yes, there are two different x's, which means you have to make two different substitutions. Then you're going to subtract just the whole f of x function. Don't forget to use parentheses and distribute the minus. This step is just algebra. You're going to do the FOIL. You're going to distribute. As we've seen time and time again, so much amazing cancellation should happen. All the x terms should cancel. Any constant terms would cancel. And you're just going to be left with the numerator terms having h and then an h in the denominator. You're then going to be able to reduce that h. And then don't forget to actually take the limit. If you don't take the limit, you're stopping at the secant line, but I need you to go all the way down to the tangent line and in order to actually be the derivative. So once you get down to that simplified version, the whole point of taking the limit is everywhere there's an h, it goes to 0, which means your final answer is 6x minus 2. Again, this entire process could have been a problem from yesterday. But now the new thing is you're going to realize that 6x minus 2 is called the derivative of f, and the notation for derivative is again that f prime. Something else to just kind of know about calculus, there are lots of different ways that you can actually say derivative. F prime of x is probably the most common, and it's the only one that we're going to use, but just know that there are lots of other different options, dy dx, y prime, and then these other kind of fancy notations. Again, you'll have fun with those next year, so we're going to mostly stick to f prime, but I just kind of want to make sure you know that it's a thing. Let's do one together, just like that other problem. So find the derivative of 3 over x. So again, you're always going to associate the word derivative with the limit of the difference quotient. So to start, this is the limit as h goes to 0. Go to the f function. Everywhere there's an x, you're going to put an x plus h. So that's 3 over x plus h minus f of x all over h. You've seen now for days and days that when you use the difference quotient, you're either going to get some simple algebraic calculation with distribution, like example 1. You're going to get fraction action, like here in example 2, or you're going to get some radical problems, in which case you have to rationalize. Those are the 3 main strategies. So I'm going to find a common denominator on the top here. The common denominator of x and x plus h is those 2 things times each other. That turns this 3 into a 3x, minus this 3 turns into a 3 times x plus h. And of course, don't forget to use parentheses. This is all still over h. So on the top, I get 3x distribute minus 3x distribute minus 3h over x times x plus h. And then because this is h over 1, the way to get rid of complex fractions is, of course, to keep change flip. So much cancellation should always be happening here, guys. If it's not, then it's a big, big problem. So these 3 x's cancel out. This negative 3h and this h can be reduced. Cancel an h from both, and you're left with just a negative 3 in the numerator. Again, I tend to get a little bit lazy, and I kind of drop my limit statement from the beginning to the end. So don't forget to put it back in. Once you fully reduced, you're now down to the limit as h goes to 0 of negative 3 over x times x plus h. And in the final step, make this h equal to 0, which means you're going to get an answer of negative 3 over x squared, because you'll get x times x. Not only is this the answer, but this is now called the derivative, and the notation is f prime of x. So again, these problems should actually be getting easier. And again, dare I say it, a little bit fun, but now you need to realize what it is you're actually finding, something called the derivative, and you need to be able to use the proper notation. Then what if I ask you to use the derivative? So this problem is multiple things being asked for. I wish that they had broken it up a little bit more. Your book breaks it up a little bit more tonight, but look at what they're asking you to do. So they're asking you to take the f function and they're asking you to find the derivative. So that means find the limit of the difference quotient. Then they want you to find the slopes of the graph at 2 particular locations. Then they actually want you to find the equation of the tangent line, which is the y equals mx plus b. So this problem is asking you for a lot of different things. So we're going to start by just finding the derivative. And again, when I ask you for the derivative, it's the limit of the difference quotient. So go to the f function. Everywhere there's an x, put an x plus h, minus the original function. That brings us down to here. Hopefully by now you realize you have to multiply the numerator and the denominator by the conjugate. Remember, the conjugate means the same front, the same back, and of course the opposite middle. On the top, it's a FOIL, but really it's first and last. So the square root of something times itself just becomes x plus h. A negative times a positive, square root times square root just becomes minus x. And then of course in the denominator, leave it unmultiplied. Cancel these x's, reduce these h's. Don't forget to have your limit statement. The book obviously doesn't drop it in each step, but if you do, make sure that you put it back in at the bottom. When you actually go ahead and take the limit by making the h equal to 0, that is going to give you your answer, 1 over 2 radical x. And again, this is called the derivative, and the notation is f prime of x. So that answers the first part, to find the derivative. Then it asks you for a couple of other things. It asks you to find the slope of the tangent line at these 2 particular points. So 1, 1 and 4, 2. Again, we saw these mechanics yesterday, but you have to make sure you know when to employ them. If you want to find the slope of the tangent line at the point 1, 1, the important value is the fact that it's x equals 1. And because you want to find the value of the tangent line at x equals 1, that means you actually want to find the value of the derivative at x equals 1, which is why this is f prime of 1. It means you're plugging the 1 into the derivative. That gives you a slope of positive 1/2. They then ask you to actually find the equation of the tangent line. So to find the whole equation of the tangent line at that point, you need a point, 1, 1. You need a slope, 1/2. And then it's up to you. So the book is using point slope. You can also use y equals mx plus b, but all they want you to do is take that point, take that slope, and actually find the equation of the tangent line at that location. Similarly down here, but now they're talking about the spot 4, 2. So again, you want to find the slope of the tangent line at x equals 4, which means you want to find the value of the derivative f prime at 4. That is going to give you a slope of 1/4. In order to find the equation of a line, you always need a point and a slope. And again, whether you use point slope or y equals mx plus b, I do not care. And then in this picture, they show you the original graph, the square root of x, and then they show you each of those tangent lines. And in tonight's homework, it's going to ask you to do that, but you can kind of just estimate. And again, really you're using it as a check to make sure that everything jives and that your answer makes sense. So let's do one more like this, just kind of broken up a little bit nicer. So same questions, but I broke it up into an A, B, C. So using the derivative. Your function is negative 4x squared. You're going to A, find the derivative, B, find the slope of the graph at the point 3, negative 36, and then find the equation of the tangent line. So again, if you're feeling good, pause and try it. If you're still not sure, then let's go ahead and do it together. So starting with f of x plus h, that means negative 4 times x plus h squared minus the entire function, negative 4x squared, all still over h. Then, we're a little bit big here, I guess, just in the numerator. So if you go ahead and do the FOIL, that's negative 4 x squared plus 2xh plus h squared. Negative negative becomes a positive 4x squared. That's just the numerator. So if you distribute again, you get negative 4x squared minus 8xh minus 4h squared plus 4x squared. And this is all still over h. Cancel out those x's. Again, that should always happen. Negative 8xh minus 4h squared over h. You can go ahead and reduce an h, and then don't forget to put your limit statement back in. So if I reduce an h, I get the limit as h goes to 0 of negative 8x minus 4h. If you actually go ahead and set the h equal to 0, that is going to tell you that your derivative, f prime of x, is equal to the function negative 8x. And that is, in fact, the correct answer. So that answers part A, find the derivative. Make sure you not only find it, but you know what to call it, and you use the proper notation. So we're going to take that derivative, negative 8x, and on the next slide, we're going to find the slope of the graph at the point 3, negative 36. So if my derivative, again, this is part B, if the derivative that I just found was equal to negative 8x, if they want to find the slope of the graph at the point 3, negative 36, the important value here is the fact that x equals 3, which means you want to find the value of the derivative at x equals 3, which is called f prime of 3. And that will, of course, give you a slope of negative 24. So that is the slope of the graph at that particular point. Then in part C, find the actual equation of the tangent line. To find an equation of any line, whether it's a tangent line or not, you need a slope and you need a point. Then whether you do point slope or whether you do y equals mx plus b, I've already shown you a couple of point slopes, so I'll show you a y equals mx plus b. So negative 36 equals negative 24 times 3 plus b. Negative 36 equals negative 72 plus b. B equals, add 72, 36. So your final answer for C is y equals negative 24x plus 36. So great problem, really kind of hopefully ties everything together for you. And again, if I was to ask you to graph this, I think it would be fairly simple for you to graph negative 4x squared and also to graph this tangent line. And again, you could just kind of estimate that. The last thing I want to talk about today is the idea of a horizontal tangent line. And the truth is, your book problems don't really ask you this in a way that I like. So we're going to do a couple here, we'll do a couple in the review, but there really aren't any in the homework section. So let's say, for example, that I already did the whole process and I had my original f, x squared minus 4x plus 3, and then I went ahead and I found the derivative. So I did that whole limit process, I simplified, and I got that the derivative was 2x minus 1. If the question says, use the derivative to determine any point on the graph of f at which the tangent line is horizontal, there's a couple of things you have to realize here, okay? Remember that the whole point of the derivative is that it tells you the slope of the tangent line at any particular location. If you are specifically talking about a horizontal tangent line, you have to remember that the slope of any horizontal tangent line is, of course, what? A 0. So if you want to use the derivative to find the places where the tangent line is equal to 0, that basically means you want to solve where the derivative is equal to 0. So the derivative is 2x minus 4. You're going to set it equal to 0. You're going to add 4, you're going to divide by 2, and it turns out that at x equals 2, there is a horizontal tangent line. That's great, but I asked you for the point on f at which that occurred. So this 2 implies that there's a point, 2 comma something, on the graph of f where that horizontal tangent line occurs. If you want to find that y value, you have to plug it back into the original. Plug it back into the f, not the f prime. Use the f prime for slope. Use the regular f for the point. So 2 squared minus 8 plus 3, that is going to give you a y value of -1, which means that the answer to this question is that at the point 2, -1, there is a horizontal tangent line. If that made sense, maybe pause and try this last one here, last problem for the day. So again, assume that here is your f and here is your f prime, your function and your derivative. We would have already done that limit process. Use the derivative to determine anywhere that there's a horizontal tangent line. Again, horizontal tangent line means you are trying to solve where the derivative is equal to 0. So in this case, you want to solve where 9x squared minus 9 is equal to 0. Add the 9, divide by 9, you get x squared equals 1. Take a square root, and of course, never forget your plus or minus, which means there's not just one location where there's a horizontal tangent line, but there's actually a second location. One of those is at the point 1 comma something, and to find the something, plug the 1 back into the original. To find the second something, plug the -1 back into the original. And if you do that, you get the point 1, -6 and the point -1, 6 as the 2 locations where there are horizontal tangent lines. And again, think what this would look like. This is a polynomial, a cubic with n behavior down up, which means it's going to look something like this, which means you're going to have one horizontal tangent here, and you're going to have a second horizontal tangent here. One, of course, is the max, and one, of course, is the min.